Hi everyone, my name is Waisuddin Ansari, a sophomore in high school. In this video, I'm going to share with you about black holes. Importantly, what is inside a black hole. Before I start, kindly subscribe, like, comment below and share it with your friends. So let's begin. The first discussion of black holes was in 1783 by a Cambridge man, John Michell. His argument ran as follows. If one fires a particle, such as a cannonball, vertically upwards, it will be slowed down by gravity. Eventually, the particle will stop moving upwards and will fall back. However, if the initial upwards velocity were greater than some critical value, called the escape velocity, gravity would never be strong enough to stop the particle, and it would get away. To understand them, we need to start with gravity. Gravity is described by Einstein's general theory of relativity, which is a theory of space and time, as well as gravity. The behavior of space and time is governed by a set of equations called the Einstein equations, which Einstein put forward in 1915. Although gravity is by far the weakest of the known forces of nature, it has two crucial advantages over other forces. First, it acts over long range. The Earth is held in orbit by the Sun 93 million miles away, and the Sun is held in orbit around the center of the galaxy, about 10,000 light years away. The second advantage is that gravity is always attractive, unlike electric forces, which can be either attractive or repulsive. Furthermore, Einstein wrote a paper in 1939 claiming that stars could not collapse under gravity because matter could not be compressed beyond a certain point. Many scientists shared Einstein's gut feeling. The principal exception was the American scientist John Wheeler, who in many ways is the hero of the black hole story. In his work in the 1950s and 1960s, he emphasized that many stars would eventually collapse and explored the problems this posed for theoretical physics. He also foresaw many of the properties of the objects which collapsed stars become black holes. The Einstein equations can be defined as a singularity. This means that at this point of infinite density, one can't predict the future. This implies that something strange could happen whenever a star collapses. Penrose proposed the cosmic censorship conjecture. All singularities formed by the collapse of stars or other bodies are hidden from view inside black holes. A black hole is a region where gravity is so strong that light cannot escape. The cosmic censorship conjecture is almost certainly true because a number of attempts to disprove it have failed. When John Wheeler introduced the term black hole in 1967, it replaced the earlier name of frozen star. Wheeler's coinage emphasized that the remnants of collapsed stars are of interest in their own right, independently of how they were formed. The new name caught on quickly. From the outside, you can't tell what is inside a black hole. Whatever you throw in, or however it is formed, black holes look the same. John Wheeler is known for expressing this principle as a black hole has no hair. People usually ask, what happens to all the particles and astronauts that fell into the black hole? The answer is that they can't just re-emerge when the black hole disappears. The particles that come out of a black hole seems to be completely random and to bear no relation to what fell in. It appears that the information about what fell in is lost, apart from the total amount of mass and the amount of rotation. But if information is lost, this raises a serious problem that strikes at the heart of our understanding of science. For more than 200 years, we have believed in scientific determinism, that is, that the laws of science determines the evolution of the universe. Is falling into a black hole bad news for a space traveler? Definitely bad news. If it were a stellar mass black hole, you would be made into spaghetti before reaching the horizon. On the other hand, if it were a supermassive black hole, you would cross the horizon with ease, but be crashed out of existence at the singularity. Also, there is a black hole with a mass of about 4 million times that of the Sun at the center of our Milky Way galaxy. But can this black hole destroy Earth? The answer is no. Earth is facing no threat because no black hole is close enough to the solar system for our planet. According to NASA, even if a black hole the same mass as the Sun replaced the Sun, Earth still would not fall in. If you fall towards a black hole feet first, gravity will pull harder on your feet than your head. Because they are near the black hole, the result is that you will be straight down lengthwise and squashed in sideways. If the black hole has a mass of a few times our sun, you will be torn apart and made into spaghetti before you reach the horizon. However, if you fell into a much larger black hole with a mass of more than a million times the sun, the gravitational pull would be the same on the whole of your body and you would reach the horizon without difficulty. So, if you want to explore the inside of a black hole, make sure you choose a big one. Although you wouldn't notice anything in particular as you fell into a black hole, someone watching you from a distance would never see you across the event's horizon. Instead, you would appear to slow down and hover just outside. Your image would get dimmer and dimmer and redder until you were effectively lost from sight. As far as the outside world is concerned, you would be lost forever. Physicist and cosmologist Professor Stephen Hawking says, suppose there was no gravity and space-time was completely flat. This would be like a completely featureless desert. Such a place has two types of symmetry. The first is called translation symmetry. If you move from one point in the desert to another, you would not notice any change. The second symmetry is rotationist, where in the desert and symmetry, if you started to turn around, you would again not notice any difference in what you saw. These symmetries are also found in flat spacetime. The spacetime one finds in the absence of any matter. However, as one moves away from the black hole, time gets less and less. Very far away from the black hole, the spacetime looks very much like flat spacetime. Because black holes have no hair, as the scientist John Wheeler put it, one can't tell from the outside what is inside a black hole. Apart from its mass, electric charge and rotation, this means that a black hole must contain a lot of information that is hidden from the outside world. But there is a limit to the amount of information one can plug into a region of space. If the amount of hidden information inside a black hole depends on the size of the hole, one would expect from general principles that the black hole would have a temperature and would glow like a piece of hot metal. But that was impossible because, as everyone knew, nothing could get out of a black hole, or so it was thought. As particles escape from a black hole, the hole will lose mass and shrink. This will increase the rate of emission of particles. Eventually, the black hole will lose all its mass and disappear. Moreover, if information were really lost in black holes, we wouldn't be able to predict the future, because a black hole could emit any collection of particles. It could emit a working television set of the complete works of Shakespeare. Though the chance of such exotic emissions is very low, it is much more likely to emit thermal radiation. It was therefore very important to determine whether information really was lost in black holes or whether in principle it could be recovered. Many scientists felt that information should not be lost, but for years no one suggested a mechanism by which it could be preserved. This apparent loss of information, known as the information paradox, has troubled scientists for the last 40 years and has still remained one of the biggest unresolved problems in theoretical physics. Finally, the black holes are still characterized only by their overall mass, electric charge, and spin outside the event horizon, but the event horizon itself contains the information needed to tell us about what has fallen into the black hole in a way that goes beyond these three characteristics the black hole has. People are still working on these issues and therefore the information paradox remains unresolved. But I am optimistic that we are moving towards a solution. Watch this space.